Welcome to today's Explainer. As first-year biomedical engineering students, you are stepping into a world where electronics and human biology are intimately connected. So let's just jump right in. Today, we're going back to absolute first principles to really understand the two main flavors of electrical power, direct current and alternating current. We're going to build a rock-solid conceptual foundation that you will use throughout your entire career designing life-saving medical devices. But before we get into the heavy science, let's start with a mystery you probably interact with every single day. Think about your smartphone for a second. It obviously needs electricity to charge its battery, right? And your wall outlet has electricity. So why do we need that bulky little power block, the charger, sitting between the wall and your phone? Like, why can't we just wire a smartphone directly into the wall outlet? Well, if you actually did that, your phone would instantly go up in smoke. Today, we're going to solve this mystery by figuring out the fundamental difference between what comes out of that wall and what your phone actually needs to survive. To get to the bottom of our charger mystery, we actually need to zoom way, way down to the atomic level. Let's briefly remind ourselves what electricity really is. At its core, electric current is simply the physical movement of charged particles, usually electrons, traveling through a conductor, like a copper wire. Now, if you have charges just sitting there doing nothing, that's static electricity. But the exact moment those charges start flowing and moving together, boom, you have an electric current. So the absolute crucial takeaway here is that current is all about movement. So now that we know current is moving charge, it brings up a really fascinating question. And this is a question that actually sparked a massive historical rivalry between brilliant minds like Thomas Edison and Nikola Tesla. The question is, do these electrons always travel down a wire in a single straight line? If I flip a switch and turn on a circuit, do the electrons just march forward continuously from point A to point B? Well, the answer to that question literally divides the entire world of electricity into two distinct categories. Let's look at the first category. Imagine a one-way street where traffic only ever moves forward. Or think of a garden hose where the water is continuously flowing in one single direction out of the nozzle. This is the physical intuition behind direct current, or DC for short. In a DC circuit, the electrons exhibit a net physical displacement. That means they actually travel from one end of the wire to the other in a single, constant direction. They just march steadily forward. And it's literally called direct current because that flow is, well, direct and unidirectional. The positive and negative poles of the power source remain completely constant. The negative pole is always negative, pushing electrons away, and the positive pole is always positive, pulling them in. This steady, one-way push is the hallmark of sources that use chemical reactions or photovoltaics. Think about the batteries in your TV remote, solar panels, or those portable power banks you carry around, all DC. Now, if we visualize direct current mathematically, let's say we plot DC voltage on a graph with time on the bottom axis and voltage on the vertical axis. Notice how it looks like a perfectly flat horizontal line. There is no variation, no oscillation. It just delivers a steady, constant, unwavering push of energy. And in the electronic circuits you'll be designing, this flat line is incredibly desirable. It provides a super stable environment so sensitive microchips can do their complex logic without being disrupted by fluctuating power. But imagine a completely different scenario. What if the charges don't march forward continuously? Instead of our one-way street, imagine tidal water washing back and forth on a beach, or a pendulum swinging left, then right, then left again. This perfectly illustrates our second category, alternating current, or AC. In an AC circuit, the charged particles don't actually travel continuously down the line from the power plant to your house. Instead, they vibrate and oscillate back and forth around a fixed point. They transmit energy through their coordinated vibration, but the individual electrons themselves just wiggle back and forth right in place. So why does it vibrate? Well, it's called alternating current because the direction of the current literally alternates, and this happens because of how AC is generated. Picture a coil of wire rotating inside a giant magnet. As the coil spins past the north magnetic pole, it pushes the electrons one way. Then, as it continues its spin and passes the south magnetic pole, it pulls the electrons back the other way. Power plants use these massive spinning turbines, which are absolute marvels of human engineering, driven by steam, wind, or falling water. And their natural output is exactly this, a continuous alternating push and pull. Because this push and pull happens in a repeating cycle, we need a way to measure how fast it's actually occurring. We measure this frequency using a unit called hertz, usually just abbreviated as Hz. 1 hertz simply means one complete cycle of pushing and pulling per second. Depending on where you live, the massive generators at your local power plant are engineered to spin at a very precise speed. If you're in North America, your household wall outlet alternates at exactly 60 hertz. That means the current reverses direction 60 times every single second. In much of Europe and Asia, the standard is 50 hertz. When we plot that continuous alternating push and pull over time, it creates a really beautiful repeating mathematical curve. We call this a sine wave. Notice how it symmetrically rises to a positive peak, smoothly falls back down through zero, reaches a negative peak exactly as the current reverses direction, and then returns to zero to just repeat the whole cycle over and over again. Okay, so comparing our two flavors of electricity side by side, DC gives us a steady, unidirectional flow, usually born from chemical batteries, and it provides that flat line voltage that's absolutely perfect for electronics. Meanwhile, AC is a bidirectional, oscillating wave, born from spinning mechanical generators at power plants. But wait, you might be wondering, if microchips love the steady flat line of DC, why on earth do all our wall outlets provide the oscillating wave of AC?
That's a great question, and the answer lies in the famous 19th century War of the Currents. AC actually won this war for our national power grids because of a frankly magical device called a transformer. Without getting bogged down in complex math, a transformer allows us to easily take an oscillating AC wave and step up the electrical pressure to hundreds of thousands of volts. Why do we want to do that? Because at ultra-high voltages, we can push power across hundreds of miles of transmission wires with very little energy lost as heat. Once it finally reaches your neighborhood, another transformer steps down that massive voltage back to a safe 120 or 240 volts for your home. DC just cannot be stepped up and down easily like this, which is exactly why AC rules the power grid.
And you know what? This finally solves our smartphone charger mystery from earlier. Remember, the delicate microprocessors in your phone require a constant flatline DC voltage to process digital ones and zeros. But the wall outlet is pumping out wildly oscillating AC power meant for long-distance travel. If you connected them directly, that oscillating wave would completely destroy the microchip. So your charger block acts as the crucial middleman. It contains components called rectifiers and converters that intercept the wall's AC wave, smooth out all those oscillations, and convert it into the gentle, steady DC flatline that your phone's circuits can actually use safely. Before we look at some specific medical applications, it is absolutely vital to drop a few common electrical misconceptions. First, as we've clearly seen, electricity is not always DC. In fact, the bulk power grid is almost entirely AC. Second, there's a really dangerous myth out there that DC is totally safe while AC is lethal. Guys, this is totally false. High voltage of either type can cause severe injury, and both require strict safety protocols. Finally, just remember that very few modern electronic devices run on raw wall electricity. Almost everything with a computer chip, from your laptop to a complex medical monitor, has an internal or external adapter silently doing that AC to DC conversion behind the scenes. So why is all of this so critical for you as future biomedical engineers? Because in a fast-paced hospital environment, you are going to be managing both AC and DC constantly. You'll design life-saving ECG machines that measure the heart's tiny electrical signals. These systems absolutely rely on ultra-stable DC batteries, because even the slightest AC ripple from a wall outlet would completely drown out the patient's heart signal. You'll work with defibrillators, which store up massive DC charge in capacitors to deliver a life-saving shock. But conversely, you'll also manage huge MRI machines that pull heavy AC power straight from the hospital grid to run their cooling systems while simultaneously using DC to power their massive electromagnets. You literally have to master both domains. Now that we deeply understand the physical intuition of how charges move, whether they're marching steadily in DC or vibrating rhythmically in AC, it leaves us with a truly exciting question for our next lesson. We know the charge is moving, but how exactly does this moving charge actually transfer power? Like, how does that movement convert into real work, whether it's spinning a motor, heating a surgical tool, or lighting up a hospital ward? That incredible translation from moving electrons to usable power is exactly what we're going to tackle next time. Until then, keep questioning the world around you.